I'm the conference chair for Global Research Conference 2020, and I will be serving as the moderator for this session. All right, so ladies and gentlemen, you will be hearing a presentation from our invited speaker, Prof. Dr. Amlan Chakrabarti. So before we start, I would like to share with the audience some background of our invited speaker. All right. So Amlan Chakrabarti is a full professor in the A.K. Chaudhary School of Information Technology at the University of Calcutta. He is also the Dean for Faculty of Engineering and Technology of his university. All right, he did his doctoral research at Indian Statistical Institute, Kolkata. Okay, he was a postdoctoral fellow at the School of Engineering, Princeton University, USA, during 2011 until 2012. All right, so he is the recipient of prestigious so many awards. To name some of it are the ST Broadcast Fellowship Award in Engineering Science, Indian National Science Academy Visiting Faculty Fellowship, the SPS Invitation Research Award, and Hamid Visiting Professorship from University of Cambridge. Okay, and he also served in various capacities in various higher education organizations, okay, both at national and international levels. About project grants, he has received multiple project grants in the area of security in cyber physical system, IoT, embedded system design, VLSI design, quantum computing, computer vision and data science from various national and international agencies. And till date, he has graduated 9 PhD students. Also, he has published around 140 research papers in index journals and conference. And he is a senior member of IEEE and ACM, right? Distinguished speaker of ACM, secretary of IEEE SIDA India chapter, okay, vice president of Data Science Society and life member of CSI India. So without further ado, okay, I would like to welcome Prof. Amlan Chakrabarti to share his talk. Okay, Prof.
Okay, very good afternoon to all of you, okay. And thanks to Dr. Aziz for inviting me, and thanks to the organizers, and thanks to all. And I hope that this is a wonderful conference, yeah. And I am very happy to be a part of this conference. My today's lecture, okay, will be in a very relevant topic, right, which is of having a great societal importance as well as having a great technological impact. So what I will discuss today, okay, will be technological computer-aided detection and diagnostics, and the technology domain will be obviously the machine learning, or rather the deep learning tools and techniques. So. Visible to all of you, right?
Okay. Yes.
Okay, great. So the title of my talk is Trends in Computer-Aided Diagnosis Using Deep Learning. Okay, so I will try to give you an overview of what is computer-aided diagnosis, and then I will let you know that some of the techniques which are very well used or which are very well referred in domain, and then I will discuss with some of our work. Okay. So before we get into computer-aided diagnostics, we need to understand that what is medical imaging, right? And why it is so important and as well as fascinating, right? So medical imaging is a process of medical imaging is a process of diagnosing without any invasive techniques, right? It is a way of non-invasive way of knowing the internal aspect of the body. Okay. So am I audible to all of you?
Yes, Prof.
Okay, fine, great.
Yes,
okay.
We can see the slide. Yes.
Yeah. Okay, fine. Sorry. Okay. Okay. So So it's a non-invasive way of trying to get information of a particular patient or a human being, and that's why it is very important aspect of medical science. And obviously, when we look into this medical imaging, it incorporates a lot of domains. Okay, so imaging itself, right, has a variety. Okay, it can be of different techniques of imaging, right? It can be of imaging of various scales, right? And it can be imaging like whether it is a static kind of image or it's a dynamic kind of image. Okay, static kind of image means you can take a chest X-ray or you can take a lung CT, which is a static image. But when you are trying to do an ultrasound, right? Okay, those are dynamic image, right? And there are others also. And if we talk about skills, it can be skills in the form of digital X-ray, in the form of a CT or MRI, and it can be in the form of microscopy, right? Confocal microscopy or any sort of digital microscopy, right? And it can be interpreted in various forms. It can be a radiology image, it can be tomography image, it can be endoscopic image, and so on, right? So so this itself is a very complex system, right? Capturing an image and setting up the equipments, okay, for a particular patient of a particular disease type is itself a challenge, right? And that's why we require specialized doctors and specialized radiologists, clinicians to handle those issues, right? Those are not strictly our domain of computer science or information science. Okay, we take the help of the doctors, and our work starts once the image is being generated, right? Uh, so now when we want to analyze these images, we have to know that that means how we can analyze, because there is no single way of analyzing all kinds of image, because we tell that this is a multi-modality imaging, right? It is of different images are being captured in different different forms of images are being captured in different of sources, right? uh, we know digital X-ray, we know a CT, we know PET, okay, MRI, and so on. Each of these type of images are called, that means distinct modalities of medical images, okay? And you see that each of the modalities, okay, here in the right, the diagram in the right, or the chart in the right, the table in the right shows that the different body organs, okay, comes under uh, different types of imaging modalities. Or rather, if you want to detect a particular disease in a particular organ, right, you need to capture uh, maybe more than one type of modalities. Okay, so I give a small example. Okay, due to the little knowledge I have in this domain, though I'm not a doctor, right? But we are working with the doctors last 6 years, so we have gathered a little bit of knowledge on this type of modalities of imaging. So let us try to understand what's the need of multimodal imaging in this particular context. Suppose you go to suppose a patient visits a doctor, right? Right, and a patient if the doctor does a CT or an MRI, right? A CT and an MRI are called structural imaging, because a CT and MRI gives information about the shape and the size and the texture of the particular lesion. So lesion is some abnormality which is there in a particular tissue, in a particular bone, right? It is called a lesion. So the structural information of the lesion can be gathered. If it is a hard structure, it can be gathered through X-ray. If it is a soft structure, it can be gathered through MRI. CT can play in between. But all this gives you structural information. But to a doctor, structural information is one part. A doctor also wants to know whether the lesion size is pretty big, so obviously it's a concern. But doctor also wants to check that whether the lesion is in the growing phase or the lesion has stopped growing. to know that the doctor has to know the metabolic activity, whether the lesion region is still having a very high metabolic activity. So to know that, the doctor has to go with functional imaging, and the functional imagings are like PET imaging. So PET imaging will give us that means a sort of glucose absorption in the particular region, right? And the rate of glucose absorption will let you know how metabolic activity is. So for a doctor, obviously size is one of the parameters to tell that whether it is whether the lesion is likely to be malignant or not. On the other hand, the particular metabolic activity of the lesion is also an indicator. A particular lesion which is pretty big but has stopped metabolic activity means that the lesion will not grow further, the lesion will not spread further, is still not much worry for a doctor. But a lesion which is maybe small in size, but which is having a very high metabolic activity, which means that lesion will grow in a very very fast way, in a very rapid way, in the particular organ, that's obviously a cause of concern. So that's why the doctor tells that, hey, go for a PET, and also you go for a CT MRI, and also you go for a PET, right? And I hope that you are now able to understand that why multimodal imaging is required, not only for one particular disease, but for one disease also. That means for one disease also you can require, okay, a doctor can require several types of modalities. Let's go into a little bit of the way the present medical houses, okay, or medical specialties, medical facilities work with this type of images. They have there is a pretty well defined standard at the present domain, and that also helps us, the people like us or researchers like us, so that we can get the data, we can work with the images, and the data, the patient data, the image data, and the doctor's inference can all be connected in a very good information platform, right? And that's why the systems like PACS, which is a picture archiving and communication system, a radiology information system, these are the systems which holds the data of this type of images, and the most popular format, which is called a DICOM format, which is used for exchanging this type of image data. Now we're looking at the more core part where my expertise lies. Okay, so now I introduce all of you to the domain of computer-aided detection and diagnosis. So the term computer-aided means that obviously the computer science people have some role to play, right? So what we do here, we try to work with this type of we take the image as our data, right, as our source data, right, as our input data, and we try to churn out information out of this data and try to help the doctors, right? And how we can help the doctors in this domain? We can help the doctors by suggesting some inference which our algorithm generates. This inference helps the doctor to get a support of what he or she is thinking about. This also classifies the images into different categories. That, hey, this patient is pretty serious. This patient is okay, it's average. This patient is not so serious. So accordingly, the doctors can divide the work, and doctors can divide the time, and that helps the doctor. Last but not the least, this also helps the doctors who are in the learning process, who are not yet a doctor, but he or she is going through a course, okay, and this can also serve as the training tools to identify or to get the information from out of these images. Okay, so what type of informations we can generate in the context of computer-aided detection and diagnosis? There are two parts of this. of this. One is called the detection, and another one is called the diagnosis. Okay, so what is the detection? Detection means it will try to localize. Okay, it will try to localize a particular deformity. Okay, which is a sort of outlier, which is a sort of abnormality. Okay, in a particular image. Right. Obviously, you can understand that these are mostly machine learned models. So the abnormality or the prediction will come from the knowledge which we have already imbibed in our system, right? And provided we have done that, right, my system can able to tell that, hey, this is a particular region where I find that there is some sort of deformity. So this is called that detection, right? And that detection is done by putting a mark. So if you see a chest X-ray image, right, you can see there is a little bit thicker patch in this region. So once I pass this image to my tool will mark this region and will help the doctor to just get a direct glance on this particular region and try to understand what it might be. Right? This is a first level of help that the computer tool can offer to the doctor. Okay, this is called a screening radiology, right? Because it screens and tells that, hey, these images have something to take care of. Okay, that means I have found some deformity in these images, but these images are fine, so you can let them pass through. So this is called screening radiology, right? And the suspicious areas are marked. Okay, and that helps the radiologist or the doctor who treats the patient, right? The second level is that going farther down. Okay, going farther deep to right. So the next level to this is obviously we are trying to generate a particular score to this particular deformities, right? And this is normally called as risk prediction. So a particular a particular deformity has been marked, and using the feature of the deformity, can I give a score, and this score is called the risk. So maybe the higher the score, right, the risk of the patient is higher, and lower the score, the risk of the patient is lower, right? And this helps the doctor, right? You know that that visualization that means either the doctor is doing by only seeing the images, or tool is giving some help to the doctor. Ultimately, the doctor, for a community approach, the doctor has to do a biopsy, right? And the doctor should do the biopsy. He or should do the biopsy of that particular region, okay, where he feels chances are very high. So unnecessary biopsies are also reduced, okay, once the risk prediction is done in a proper way. That is assuming that my prediction is very good, is very proper, is very high accuracy. So what it will help? It will help the doctor to identify the risk and accordingly do the biopsy of the high risk regions or high risk deformities of the particular patient, so that if the biopsy can be justified, and that's also one of the reason, and so the way it tries to generate the data is in the form of some sort of score, right? And this score is given here, right? It can give the shades to the region. Shades defines a particular score, or it can give value to the particular region as a form of a data to the doctor. So these are the visualizations which the computer-aided diagnosis tool tries to do, right? And that's why it's called computer-aided diagnosis, and that's why very interesting. Though it seems to be a pretty. I've told it within a couple of minutes what it is, but to generate a model, okay, and to generate a higher accuracy of this type of models, okay, we require a good amount of data. We require a very good help from the doctors, right, who will initially supply all the domain knowledge, and we need to generate very good computational algorithms so that the accuracy and the knowledge abstraction is pretty perfect or pretty good, okay, efficient, right? So so thinking the complexity of these particular domains, right? Though we know traditional machine learning is existing for maybe for the last 15 years in this domain, right? But for the last 5 years, we have seen a predominant use of the deep learning techniques here, right? And we know that what is a deep learning technique and why it can perform better than a normal machine learning type of approach. Because we know that in the case of deep learning, the feature selection or the feature space creation and classification goes in a seamless way, right? The initial stages are the generation of the feature feature space, right? Or the feature parameters, and then based on the parameters or based on those parameters, the decision of the classifier takes place, and that is done in a very seamless way. We don't need to abstract the features at first and then feed to the classifier or predictor at the second stage, right? So this automatic feature abstraction and followed by classification helps the deep learning to capture to reduce the error which is very much which happens in a normal way when we take the feature extraction as a separate job and then generating the classifier in the traditional machine learning approach. And we all know that this particular deep learning is a process where we are trying to imitate the processing what is done in our brains, right? And we know that human brains are one of the that is the most strong processing resources in the world, right? And why it is so strong? It is so strong because it has different functional regions. Each of the functional regions generates different abstractions, right? And it is a different types of feature space. Okay. It analyzes the data in the different feature spaces, right? And these feature spaces are ultimately clubbed and abstracted, and then the final decision has been taken, and that is imbibed in the deep learning stages, right? And that's the way the deep learning network follows. It is okay. That means it is a neural network model which is much improved, okay, and much dense and much deeper, okay, and which makes this particular deep network. I'm not going to details of this, right? But this is pretty standard. So this is the way how the deep networks for the computer-aided diagnosis or detection works. Okay, that means you actually that must have different types of convolution filters, and this convolution filter generates each of the convolution filter is trying to extract a particular feature. Okay, that means trying to find whether a particular feature has existence in the particular spatial region, right? And this convolution filters also works in spatially, right? It actually fragments the image into different patches, and on each convolution filter works out and tries to find whether a feature is existing in a particular spatial region or not, right? And a particular layer in the convolution kernel, a particular layer in a particular convolution network defines a number of convolution kernels, and all the convolution kernel in together generates the information of the feature space, which is defined by the features extracted by each of these kernels, right? And there are standard techniques of representing it. It is in a lower dimension using the pooling layer, and then trying to fire the feature values which are actually contributing by using using an activation function also, and then it goes on and on in multiple layer, and ultimately the very top level feature map is created at somewhere in the last layer, where you can now take a decision, right? And that's and then you take a decision using a classifier or a predictor like a softmax, and you try to okay, this is a fully connected network at the last stage of your CNN, which gives you the prediction and classification result, right? So this is a CNN. So there are other types of networks also in the deep network, but due to limitation of time and not getting into details, you can go to the RNN, which is a recurrent neural network, which works for a sequence type of data. If you have some sort of dynamic image or some sort of video image, you can work with RNN. Or if you are trying to find the sort of a relationship of a patient between the past images and the present images, how much they have changed, also you can use RNN. There are techniques like autoencoders, okay, which can represent the initial feature space in a much lower dimension due to its latent space type of property, latent feature extraction property. And there are also that means there are also techniques like generative adversarial networks, where we try to generate the information through a descriptor type of it's a generator and a discriminator type of workflow. Okay. So now I will just get into some of the very good recent works which has come up. Okay, this domain, and this is a very fantastic work for references. You should look into this work. So I told the CNN is the baseline, right? When you try to work with different type of aspects of your computer diagnostics, you can do segmentation, right? You can do localization, right? You can risk prediction, and all sorts of things you can do. So this is a work which was done in the basically segmentation and localization, okay, together. So the work was to actually segment out the vertebra and try to localize that. So vertebra is a very important part of our body. A lot of diseases actually occurs due to the deformity in some of the vertebral segments, and each of the vertebral segments are pretty important, because depending on which vertebral segment has been affected, based on that the doctor has to take a decision, right? What needs to be done. So this particular work, which was published in 2018, okay, this gives you a different type of feature space extraction. What it does, it actually, that means, works with different scales of images in different networks, right? So there are 3 networks, right? And each of the networks works with different scales of the images, because there are different layers in the particular vertebra. So that means so each layer is good in different type of scales. So now each of the scales are passed through a network with a series of convolution filters, and then there is a concatenation, right? And this concatenation, and also there is something, is that it is actually generates on multiple slices. So normally when we try to take a 3D information, because all these structures are 3D structures, it doesn't play a good role if you only take one plane information of the structures like vertebra. So for the 3D structures, you have multiple slices, right? And these multiple slices are work together in this type of networks of 3D volume, and then they generate, and then they concatenate the information in the multi-scales, right? And then they generate the entire information of the vertebra, which is a concatenation of the information coming from multiple scales, right? And that's a fantastic network, which is called okay. So for intervertebral disk detection and localization, because this is a important body part, the vertebra, very important body part for many of the diseases. This is also pretty important. This is a work which was done for brain. Okay, brain lesion. You know that brain lesion is a brain tumor is so much that means of so important, and it is so common nowadays, right? So they have also tried out with different techniques. They have tried with one high resolution and one low resolution, and try to work with both the resolutions and try to concatenate these resolutions and try to so why this is required, because we know that the feature so resolution defines a spatial constraint. So when we have a high resolution, means you are taking more number of samples in a spatial region. When you're taking more resolution, it means that you are taking less number of samples in a spatial region. So if you are trying to take a gross feature, you can take it a low resolution, right? If you take a very fine features, okay, you need to take a normal resolution or a very high resolution. So different resolutions, okay, gives you different opportunity of sampling, okay, different sample space distribution, and that is so important in any particular neural network context. So sample space distribution changes, and in a different sample space you have different types of features. So you have to take both the features and try to analyze them and try to make a generate constructive features on this particular way. Okay, this was one of our work, okay, which is pretty good work we did. This is the MICAI Gleason Challenge. MICAI is the top conference in medical imaging, okay, medical imaging, and they open up challenges. So 2019, right, the challenge was that to generate the Gleason score. So Gleason score is a histopathological image of your prostate. So the Gleason score gives you, that means how much this particular tissue is cancer, right? So higher Gleason scores means higher cancers, and different shades give different type of Gleason scores. So the challenge was it gave a very limited data set, and using a very limited data set you have to solve a complex problem, right? And that was the challenge. So the way we try to do it, we sort of transfer learning, right? We use a type of convolution neural network, but we use a transfer learning. So in the case of transfer learning, what we try to do, a convolution network tries to generate the feature space for your problem domain and tries to solve it. But in transfer learning, what you try to do, you try to use a different, that means use a data set which might not be exactly in a problem domain, but which is larger and somewhere related, but not exactly. So you try to train your network with a more holistic, with the features which are available from your large supply database, right? And then you tune your network. Okay, then you tune your network with the special with a limited amount of data set what you have, and that is called transfer learning. And you can use a convolution encoder decoder. This is the way the encoder decoder works. It actually tries to compress the feature space, okay, and tries to have a compressed representation of the feature space of your input, right? So how it works, this compressed feature space actually helps you to understand the most important features of your data, right? And that also we have used in this particular work. So our work actually gave a good result, and it was listed as the solutions of the MICAI Gleason Challenge 2019, right? And we have successfully solved this. So they list the top solutions in this domain, right? Right, and this is last but not the least. This is the COVID net, which is the new net which has come up with this pandemic, the pandemic scenario of COVID. People are trying to generate the deep network solutions which can try to distinguish between a normal patient or a not affected person with a COVID affected person, and vis-a-vis a normal pneumonia person. So because this is a first detection, so if you can detect within chest X-ray, you can detect it within minutes. You can detect whether the person has a COVID or non-COVID, and accordingly you can go for the treatment. but the other type of diagnosis takes a bit of time. So the patient can be it can be in a serious condition. Okay, that means if we have to wait for some time. Normally, it's a 1 day you need to take to go through the entire test, right? And that time may be also very crucial for a critical patient. Though this is not yet, I will just tell you that though this is not yet that means a very that means a very well supported still in the medical community. Okay, but a lot of works have been going on. Okay, in this particular domain, right, where people are trying to use the deep learning techniques to just chest X images, right? And this is one of the network which is being proposed by a group. Okay, this is called a COVID net, right? And it uses a little bit of feed forward lighter convolution network. The kernels are pretty small, and you see the 1x1 convolution kernels, which are pretty small kernels, and but still it gives you a good result. I think this reports around 90% of accuracy. Okay, so these are some of the very existing work using the deep networks, right, which has helped us okay, in the domain of computer-aided diagnosis. And I think this is increasing. If you see the last 5 years, a lot of deep network-based activities have been initiated, and a lot of good results have come up. So I will. So I think that I'm pretty close to my lecture duration, and these are some of the works what we are doing in my research group. That if you are interested, if the participants, if the faculty members, researchers who are there in this particular conference, if you are interested, please connect me to my email ID. That means in this year itself, we have published some good publications, which incorporates a lot of activities, a lot of collaborations with the doctors, and we're working on 3D reconstruction from the 2D MRI slices. Very important problem, and which is a very good problem in a sense that it reduces the time of showing. So we are generating the 3D okay, from the 2D from the 2D information with the faster time okay, than the present algorithm, than the latest algorithm gives you, right? We have also done some good work in the localizing some deformities okay, in terms of colon cancers. We have done good work in terms of lung nodule detection. Okay, pulmonary lung nodule, because in the Southeast Asia, a majority of our patients are that means a lung cancer, because due to our pollution, and as well as due to our smoking habit, right? The lung cancer is very predominant, and our CAT tool actually does an early detection, so it can detect a very small amount of also, right? And those are one of the good works we have done. We are trying to localize. We are working with 3D, as we have already told. We are working with spine image. We are trying to also trying to denoise the images in different ways. This is a very important work which has come up in this journal in this year, where we are the first group in the entire world, right, where we have actually detected the sub-centimeter pulmonary structures using your computer-aided detection. So sub-centimeter is a very small nodule, right, which normally doctors take a good amount of time to look in, and only an expert doctor can do this. So our technique was successful. The successful detection of this particular sub-centimeter nodule using a machine learning, right? And this machine learning technique was called a penalized regression technique, right? And obviously we have used some sort of fuzzy data also for denoising of this CT, of these chest X-ray images, because chest X-ray images are chest X-ray images. The working chest X-ray images is very important in the doctor's domain, because chest X-ray is the least cost imaging modality. Okay, CT, MRI are very high cost imaging modality. So if you are trying to serve masses, you have to work for chest X-ray. But the problem in the chest X-ray is that they are not being captured very high-end equipments in many of the cases. So normally the chest X-ray data itself has very good noises. So if you have to do a real detection, you have to first of all clean up the chest X-ray images. Remember, there is also a caveat. The caveat here is that, but there are some shades which are inherently the shades which are not from the noise. These shades are due to the disease of the patients. So you have to understand what is the noise X-ray and what are the other patterns which may be very close to the noise, but they are actually the disease patterns. So this makes a very good problem of actually doing the computer-aided diagnosis on the chest X-ray. And we have done a very good work here, and this is one of the highest impact factor journal in this domain. We have got our paper 2 here. So last but not the least, in my conclusion, I want to tell that that is computer-aided detection and diagnosis started for the last, I think, 10 years. Okay, it has been robust for the last 5 years or 3 to 5 years. It is now working in a very robust way. The deep network techniques are giving a pretty good handle for us to do that. But there are challenges. Data sets are not pretty available in many of the cases. Okay, like COVID-19, you don't have much enough data sets from all the different parts of the world. That means you require doctors who will give the information for annotations of leveling of the images, so that you can make the database and you can make the training data set, right? And obviously you require domain experts, as I told, right? You require a significant amount of time to knowing the data itself. When a student comes or a researcher comes to me, hey, I want to work with you with a particular type of disease, right? A time gets spent, okay, to know the particular disease, to know the particular type of images, to know the particular patterns of disease patterns in those type of images, and that time you have to give, okay, to start working in this particular domain, right? And obviously noises are there, and you know that this type of biomedical radio images are taken by different types of equipments, different standards of equipments. So it varies a lot from a medical center A to medical center B, right? And obviously heterogeneous classes, which means that there are different types of, that means if you only tell me, if you go to a doctor and tell that, hey, can you tell me that with pulmonary lung nodule is what are the classes? You can have so many. You can have that means where the nodule is located, in which particular lobe of the lung it is located, right? Whether it is on the muscle, whether it is on the tissue, whether it is on the bone, right? Based on the location, based on its appearance, based on its texture. Different classes are being identified by the doctors. So now our computer-aided detection has also identified the same classes, and that's also a big challenge, because otherwise it will be not acceptable to a doctor, right? So this is the biggest challenge, because there is so many heterogeneity in identifying the deformity itself, and that's also one of the predominant challenge in this domain. So there are challenges aplenty, but it has a huge societal impact, and obviously now we have the tools like deep networks and good processing systems, which can give us a leverage to work in this very challenging domain of technology. Okay. So yeah, so class imbalance problem, sorry, I missed it. Class imbalance problem means that many of the cases you will get the data, but the data is not enough for all different types of disease types. Maybe one disease type is pretty predominant for your training data is pretty good, but for other disease types the training data is not very good. Or maybe healthy patients data is good, the disease patient data is very small. So the ratio of the data of the different types of classes for which you require for training are not equal. So you need to take different types of sampling techniques, undersampling and oversampling techniques in your training data set to handle this type of problems, right? And again, the limitation of time, I cannot get into the every details of how the problems are handled, but obviously there are techniques by which you can handle these challenges. So last but not least, I thank my research group. It is a very vibrant research group, very very motivated research group. Many of them will be graduating this year or maybe next year. But this is a group which is we have got funded projects. And welcome the international students and international scholars and faculty members to connect us so that we can have some good research also in collaboration. So thank you all. For the questions, I will be happy.
All right. Thank you very much, Prof. Amlan, for addressing the very interesting topic. Okay. I would like to welcome our Deputy Chair of Global Research Conference, Prof. Helmi. So, Prof. Helmi, is there anything that you would like to say?
Okay, thank you very much for the chairman. Hi, Prof. Amlan. How are you?
Yeah, good afternoon, Professor Helmi.
Yeah, it's very,
nice to meet you here.
Very interesting topic that you presented. So I'm just curious, how do you handle the spec of the computing in the process of the huge amount of data using the deep learning?
Yeah, so that's a very important question now because we have to scale up our computing storage and computing processing capability. So we have that means a mini cluster, okay, at presently, which is a mini HPC, okay, which is a which is a system having around 48 cores, okay, cores, Intel CPU, IBM mini cluster. This was the machine which we worked for from 2014 to 2018. But 2018 onwards, we have actually made a very bigger HPC, right, which consists of around 1024 cores, right, having a good amount of GPU facility, right, and obviously for the database, we are taking the help of our medical houses, right. They are providing us the storage for the database because they have to do it for their own purpose. So we are trying to have a sort of virtual connectivity with them and try to store their data which they are providing us, and we are trying to process the data at our thing. So yeah, so I think, but more and more the research will ultimately go into the cloud domain, and people will work in those type of facilities. I think this particular they will get all sorts of facilities like GPU and TPU. Though handling medical data, I didn't mention much on this. Handling medical data itself has some protocols, right? There are some ethical protocols which we need to obey, right? Because the data which is taken from the hospital needs to be used only for the purpose for which I am granted. I cannot use it for other purpose. I will give a very small example. Suppose I give you blood for some testing of maybe malaria parasite in my blood, right? It is fine. That means I have given you permission to use the blood to make a device which can detect the malaria parasite from my blood. But you are not supposed to analyze my blood to get my genetic data. So if you are trying to do that, you are then breaking the ethical approval. So when you work with the medical data and you are trying to put it in a storage and you are trying to put it up in a use for some of the group of researchers, every researcher in the group should be very well aware of the medical ethics, and that's okay, fine. And that's the way we first train our students. Yeah, right. It's a very good question. Handling and processing medical data is really a challenge, but I feel that processing technology and storage technology, the way it is progressing, this we can meet up.
All right. So thank you. It's a very good answer. So is there any challenges as well regarding the pre-processing of data? Because we have some various kind of data in the medical, right?
Yeah, so processing of the data has a lot of challenges. Basically, the class imbalance is one of the challenge we face. We face a loss, face a lot. Okay, there is a very latest work which is done by a group from MIT, where they're using a sort of a generative adversarial network. Okay, to generate a very close similar data, okay, from your label data, because many of the time we find that the label data set is very less. So we need to do data augmentation, or we need to use transfer learning. But when you do data augmentation, you need to be very sure that the data augmentation is actually as per that means it is within the required variations, or it can generate the required variations what is required to make my model very robust, right? Okay, and then the next level is that means how you define this type of class levels to the data, right? And to do that also, you can use some sort of semi-supervised technique also, right, to generate a sort of auto labeling of the data. So these are some of the things which you need to apply. Okay, data augmentation, semi-supervised techniques for data auto labeling the data. This you might need to do it because sometimes you don't have a good number of doctors to help you to generate the knowledge what you need to learn, make your machines learn. Yeah.
All right. Thank you. Maybe perhaps we can collaborate later on.
Perfect. That will be perfect. I am open to collaboration, and I will be very happy to do that. And we know that South Asian countries have a very similar type of health problems, right? And so we can together we can solve the problems of multiple countries, right? And that will be a good way of doing a collaboration in scientific research. Yeah.
Okay. So any question from others? No, so I hover back to the chair.
All right, thank you, Prof. Okay, and congratulations for your achievement. All right, so we will post your talk, okay, in our YouTube channel. So maybe after this, you can get many more questions, all right, from our YouTube channel. So with that, okay, we end our session, and thank you so much, Prof, for your
Thank you.
commitment to Global Research Conference.
Thank you, Prof.
Thank the organizer. Yeah,
Okay.
thank Dr. Aziz, thank Professor Helmi for inviting me. Okay, that means, and I hope to meet you all. That means once the
Yes.
pandemic gets done, that means Malaysia is very close to me. I visit Malaysia normally once in a year with different type of assignments.
Yeah.
But this year we cannot meet. Actually, I was supposed to be physically present as per Professor Helmi's invitation. But we hope that we will connect soon.
Yeah.
Yeah.
Thank you all. Thank you.
Thank you.
Thank you, and stay
very much.
fine. Stay fine.
Yeah.
Stay well.
Yeah, you too.
Thank you very much.